Hey guys, so this is not really how I wanted to have to do another lecture this week, but sometimes life just happens. And we really need to talk about tonicity and osmoregulation before next week because we are going to have 3 labs next week all about those 2 topics, and so we have to have the background info to get us to a point where we can do those labs. So we are going to talk about how water moves around a cell, okay, and why it's so important. So, osmosis specifically, and this hopefully is not the first time that you're hearing this word. I know I hit it up pretty hard in my biology classes, but osmosis is the facilitated diffusion of water through aquaporins, okay? So we talked yesterday, facilitated diffusion, high to low, no energy, and it has to be things that won't just naturally diffuse through the membrane itself passively. Water, great example of that because membrane has that big lipid layer in the center and water will not interact with that. So specifically we're talking about these aquaporins, type of, transport protein. So normally, if this was our situation, move me. So we have like inside and outside, okay? There are 1, 2, 3, 4, 5, 6, 7 water molecules on the left side of this membrane, and there are 3 water molecules on the right side of this membrane. So if we let them do facilitated diffusion, they would want to equal out. So a couple of these would move over here until it was equal on both sides, okay? Now, those molecules will continue to move back and forth, but you're always going to have a rough equal amount on each side. So in this case, there's 10 total molecules. The molecules may be moving back and forth, but you're still going to have, most of the time, 5 on each side. They want to be equal. They want to diffuse to equilibrium. Okay? But what if we have some other molecule in here that is messing with these waters? Okay, so we have 3 waters on this side, and we still have 7 waters on this side. However, we have 2 of these pink molecules that have tied up these water molecules. So they're still over here, but we only have 1 free-floating molecule of water. So even though it is 7 on this side, that's like backwards and hard to do. So even though there are technically 7 water molecules on this side, only 1 of them is free. And there are 3 free molecules on this side. So even though you have more water over here, you will actually get a movement of water that way. It'll move this way. Because it wants to equal out the amount of free water as well. Okay, and so that's what we're going to be talking about today, is what happens whenever you add solutes to the situation. So, when in a solution, solutes decrease the concentration of free water, okay, those free water molecules, because water will often form what is called a hydration shell around the solute itself. So this is like some big globby molecule. The water is going to form a bubble around that molecule because its polarity, it's interacting with it. And this is why water is so good at dissolving everything. It's the universal solvent because it does this kind of stuff. But what that means is that you decrease the amount of free water molecules in the solution. And so there's a really cool experiment that hopefully we're going to recreate where my lights went out, where we have, equal amounts of water on both sides, but because there's technically junk over here that is removing free water molecules, the water will actually move into this side and this level will go up and it will become unequal over time. So the fancy way to say that is water moves from areas of high potential and low solute to areas of low potential and high solute. Okay, so potential is just the way that we say free water molecules. Okay, so over here on the left side of this membrane, they have like a big U-tube. And then they have this permeable membrane here that the water can move through, but these solute molecules cannot. you have 100% pure water over here. All of those molecules are free to interact. So this has a very high water potential, okay? And so we'll get into it a little more next week because we're actually going to use this kind of like these things here to calculate the water potential. This is a psi, I believe, and it's how you calculate water potential, how you represent water potential. So we'll get more into that part next week. But over here we have pure water, very high potential, and no solute over here. So we're going to move from this high potential over here into this lower potential because we're looking at how much water is free, okay? When I'm doing these kinds of questions and problems, I'm working with this as a thought, I always have to take it back to the water, okay? Because when I start to think about like the solutes on this side, and there's like, 20 solutes and 0, so you'd think it would go this way, but it doesn't because we're talking just about the water. And, these big solutes can't move through that membrane. So, all right. So, the term tonicity is how we talk about the solutions themselves. So if we have two solutions that are separated by a selectively permeable membrane, like your cell membrane, we are then referring to tonicity, okay? So the way that we talk about a solution that is high in solute and low in potential is we call that solution hypertonic, okay? So out here, we have a solution that is very low in potential and high in solute, okay? So think about like, I don't know, I always think about like maybe there's, 20 water molecules. How many of those water molecules are going to be bothered by these solutes and how many of them are going to be free floating compared to over here? There's a lot more solute over here. There's a lot more stuff to interact with the water, so the water is going to be less able to move around because it's already interacting with all these solute particles. Okay, versus over here, there's not very many solute particles over here, so there's going to be more water that's free to move around. Okay, so water will always move into a hypertonic solution via osmosis. Okay, you always want to balance out the amount of water. So if it helps to think about it, like a lot of times I'll think about it too like it's like sweet tea or Kool-Aid. Okay, if you have a solution that has 1 cup of water and 7 scoops of Kool-Aid versus 1 cup of water and half a scoop of Kool-Aid. Okay, this over here has got considerably less free water because it's having to mix with all that Kool-Aid. Versus over here, you're going to have watered down because there's still free water there. All right, so a hypotonic solution is the opposite of a hypertonic. So a hypotonic solution is one where we have very low solute and very high water potential. There's a lot of free water out there to move around, so water moves out of a hypotonic solution. Okay, so again, we have lots of water and only 2 solutes, and over here we have 4 solutes. So water is always going to move into that higher or that lower potential to try and equal out. Now, isotonic is how we talk about an equal potential. Okay, so both sides have, similar potentials and similar solute concentrations. So there is no net movement. That doesn't mean there is no movement. You're still going to have movement in and out. Things are still going to be, diffusing across that membrane, but you're not going to have any net movement, no like total movement. Okay, so every time one goes in, one goes out. There's no net change. Okay, so I want to do a little bit of practice, and it's hard to do with me not being there, but it'd be like that. So let's say I have a cell here, and inside the cell is 20% starch solution, and I put that into 100% distilled water. Which area has a higher potential, inside the cell or outside of the cell? So the way that I would go about figuring that out is I have 100% water out here, and I only have 80% water inside. So that means that my free water is on the outside. water will always move from high potential to low potential. So my water in this situation is going to move into the cell. Okay? So if I have this situation where I have a 5% starch solution inside and a 10% starch solution outside, what I really have is 95% water and 90% water. So which has the higher potential? Well, it's the outside. Wait, no, it's the inside, excuse me. Water will move outside. So this has the higher potential because it's 95% water, and they want to get to be equal. So water will move out of this cell to try and dilute this solution out here. So what if we have a 17% starch solution on the inside and a 17% starch solution on the outside? Which has a higher potential? Neither. They're both, what is that, 83% water? So where will the water go? In and out, but at equal amounts so that there is no net. Okay, so you don't have a grand total of movement. So one of the things that I want to tie this back to, and like just is cool, is osmoregulation is how plants get water. And we're going to do a lab on this next week. But again, back to our surface area. This is a picture of a germinating seed, and this is its taproot, and these are all of the root hairs. So roots will form these very, very fine, they look kind of like fiberglass or spider web hair structures. It's not very common to see them because if you were to plant this, these would be in the dirt, and when you pull it out, they're really delicate, so a lot of times they break off and stay in the dirt. But plants have these really delicate root hairs on their roots, and it increases the surface area. So what plants will do is they will take minerals and, ions and things like and nutrients, and they'll put them down into their roots, which increases the amount of not water in the root. So water from the ground moves into the root. And so that's how plants can, drink without having muscles or brains or anything like that. Like you get water by just, drinking it. Plants can't because they don't have muscles, they don't have the nervous system there to facilitate that kind of coordination. So what they do instead is they put all of their, ions and stuff down in these root hairs so that it changes the tonicity of the environment so that water actually moves into the plant, which I think is really neat. So, when we come back next week, we're going to do a lab on plant transpiration and, like water content. It's going to be really fun. I'm really excited about it. So, that is it for tonicity and osmoregulation. You have another assignment on Google Classroom. It's just to go to AP Central and do some of the review questions for this chapter. They should be assigned to you on there. So, yeah. If you guys have any questions, feel free to email me. And I will see you guys whenever we come back to school on Monday. Bye.